Okay, so this lecture we are going to be talking about, again, analysis of variance. This time we're talking about two-way independent samples ANOVA, and specifically the computation and application of the two-way ANOVA. So we will compute and apply the two-way independent samples, or factorial ANOVA. So just to recap, two-way ANOVA compares means from independent samples, right? And it analyzes how two or more independent variables influence one dependent variable. So we have several steps that go into this process. Step one, state the null and research hypotheses. This is very common for any statistical procedure. Define the critical region. Compute the test statistic. And compute the effect size and describe them. And then summarize the results. So let's go back to our example scenario that we talked about in the conceptualization of two-way ANOVA. Mars is interested in launching a new color of their M&M's line. To do so, they're going to experiment with two colors, pink and purple, to identify which color is most attractive to consumers. They are also interested in finding out whether there are differences among those consumers who like chocolate versus those who don't. So let's talk about the design. Mars first asks consumers if they do or do not like chocolate. If they then randomly place those who like chocolate and those who don't in one of two rooms, the pink and purple rooms, respectively. Each room has a bowl of pink or purple colored M&Ms. This makes it so that some people who like chocolate are in the purple room and some are in the pink. Same for those who don't like chocolate. So to measure M&M color attractiveness, they count the number of M&Ms eaten for each participant. And so we have our raw data here, right? So there are 8 people in each group across 4 groups. That gives us an N of 32. So each cell in this case represents a different consumer, so a different person placed in each group. The number here represents the number of M&Ms eaten. We have an N of 32, and we have 4 different groups. So again, this is a factorial design, right? So we have if we aggregate all that data, we have a mean of people who don't like chocolate in the pink M&Ms group of 9, so they ate 9 M&Ms. People who don't like chocolate in the purple M&Ms group ate on average 7 M&Ms. For those who like chocolate, on average in the pink group they ate 16 M&Ms, and on average they ate 10 M&Ms in the purple group. And so this main effect thing here, also called the marginal means, aggregates this information, right? So 8 is 9 divided by 7. 13 is 16 divided by 10, right? So we just aggregate the data. And moving forward, that'll give us our main effects for chocolate, for liking chocolate, and for the color of M&Ms. And you'll see what I'm talking about when we get there. So we need to state the null and research hypotheses. Well, that was weird. So first we need to state the interaction effect, right? So we're going to state several null and research hypotheses for this. First, the interaction effect. So the null for the interaction effect is the effect of M&M color on the consumption of M&Ms is the same for people who like and dislike chocolate. So what we're getting at here is we're putting in both independent variables, right? So we have the effect of M&M color is the same on M&M consumption, right? So that's the dependent variable, is the same for people who like and dislike chocolate. That's our second independent variable. So we have the 3 elements here, 2 independent variables and the dependent variable. The research hypothesis simply states that something is different here, particularly with the interaction effect. So what we're saying is the effect of M&M color on the consumption of M&Ms is different for people who like and dislike chocolate. So what we're saying is there is an interaction effect between the 2 independent variables. Well, that's unfortunate. So we also need to state the null and research hypotheses for the main effects, right? So let's talk about the null hypothesis for color, for M&M color. So the null hypothesis in this case would be the number of M&Ms consumed by those who received pink M&Ms and those who received purple M&Ms is equal. Right, so this sort of goes back to our one-way ANOVA. This is very similar to our one-way ANOVA. We're simply looking at the one variable, the one independent variable, and how it influences the dependent variable without regard to the second independent variable, right? Our research hypothesis is the number of M&Ms consumed by those who received pink M&Ms and those who received purple M&Ms is not equal. Okay, so in this case, we're making the statement that the two groups are not equal. The pink and the purple M&M people are not equal in the number of M&Ms they consumed. And so we're looking, when we're talking about the main effect, we're looking at these differences, right? So we're stating a null research hypothesis with regard to these differences, the pink and the purple M&M people. Okay? That's annoying. So we need to do the same thing for liking chocolate, right? So again, we're doing very similar idea with the color, except this is with regard to liking chocolate. So we're just looking at liking chocolate and how it influences the consumption of M&Ms, right? So our null hypothesis in this case is the number of M&Ms consumed by those who like chocolate and those who don't is equal. So we're saying they're the same, right? It's going to be relatively similar. The research hypothesis, on the other hand, is going to state that the number of M&Ms consumed by those who like chocolate and those who don't is not equal. So we're stating there is going to be a difference there. And so again, we're looking at this main effect, right? So we're looking at whether they do and do not like chocolate and asking, is that significantly different? And we're creating a research and null hypothesis based on that. So now we need to define the critical region. So in this case, there are three critical regions. There's the interaction effect, the main effect of color, and the main effect of liking chocolate. So again, there are three critical regions, so you should get three numbers based on this. Sometimes those numbers are identical, which you'll see in this case is true. More often than not, they're not identical, so we have to be very aware of that because we need three critical regions. And these critical regions are defined by degrees of freedom. So just to note that I'm going to use some notation here, so just so you're on the same track. I'm going to use the letter A, big or little letter A, as the number of levels for factor A. So this is M&M color, right? So for the first independent variable. So A is going to equal the first independent variable of M&M color. B is going to equal the factor B, so liking chocolate, or the independent variable of liking chocolate. So B equals the number of levels or groups for factor B, right? And then N is the number of people in the study. So we know this is 32. So these three elements I'm going to use to find my critical regions using degrees of freedom. So again, just like the degrees of freedom with one-way ANOVA, two-way ANOVA uses the same table, right? So the table in the back of your book, I believe it's Appendix C. So we need to first find the critical region of the interaction effect, step 2A. And that's calculated by the degrees of freedom of the numerator, which is df A times B, so the number of groups for group A, the number of groups for group B, right here. We create those numbers, we calculate the sum of those numbers, and we find 1. So we find our little 1 right here in the numerator section of the table. Then we need to find the degrees of freedom of the denominator, and that's calculated by the degrees of freedom of the within variable, and that's calculated with this equation here, n minus A times B. Again, A being the number of groups for variable A, B being the number of groups for variable B. We run that calculation, and we have 28. So this gives us our critical region of 4.20. So this helps us look for whether our F values fall beyond that critical region, right? So 4.20 is our critical region in this case. We need to do the same thing for the main effects. So for the main effects, it's the degrees of freedom of the numerator, which is DFA, or the number of groups for A minus 1. That gives us 1. DF of the denominator is the DF of within, which is calculated by the same denominator as the interaction effect. And that gives us 28. So this is actually the same for both groups, but we need to do this for however many main effects you have, right? So if you have 2, you should be doing this twice to get the critical region of 2 for both main effects. And again, we have 420. So oftentimes, so the sums of squares can be calculated. So we're just going to skip a few steps here and go straight to calculating the mean squares and the F-statistic. So oftentimes, the sums of squares can be calculated, and you can find that in the back of your book in one of your appendices. Because of it can get a little overwhelming, as I've said. So what we want to do is we want to start using SPSS to calculate our sums of squares. So the point here is really to understand what this F table is telling you, not necessarily the calculations of it. The calculations of it are important, but they're not so complex that they're impossible to do and that you need a lot of guidance. So what's here in these later calculations is available up front here. So it'll help you calculate each of these in sequence. So what we need to do is we need to basically complete this table. We need to calculate the F-statistic. And so I've done that here. So this is the final F-statistic. And this is calculated very, very similarly to what you did with the one-way ANOVA, right? So we're using the same formulas here. So this is the sums of squares of A, so color, of group A, sums of squares of group B, which is chocolate-like, sums of squares of A times B, so we have 32, right? So these numbers can be calculated using this information here. So I'm not going to go through and calculate each one of these separately. I'm going to provide the data. If you have questions about how to calculate those, please talk to me or talk to your peers, or look in the back of your book. So use your book for a reference for this. So we're trying to ask the question here to think about this statistically and conceptually. Do the F-statistics fall beyond the critical values that we computed above, right? So do they fall beyond our 4.20 values? And the question is, yes, they do. They do fall beyond the 4.20 values, right? So they're greater than 4.20. So what we need to do is summarize the results. So the elements we need to supply in the summarization was there a significant interaction effect? If so, describe the pattern in 1 to 2 sentences. Also, was the first and second main effects significant? If so, describe the pattern. And so here's what we get with the summary statistics. We need to plug all of these things in. So what we would say if we were to write this up for a publication or for class or something like that is there was a significant interaction between M&M color and liking chocolate. So our F, our degrees of freedom of the within, degrees of freedom of between, or excuse me, switch that, between and within, equal 5.90. P-value is greater than 0.05, mean standard error, our eta, right? So this gives us all the data that we need. The important part is, though, making sure this makes sense, right? Making sure that it conceptually makes sense, that somebody can look at this and know what happened in this study. The results indicate that consumers who did not like chocolate ate an average of 9 M&Ms if they were given pink M&Ms, and 7 if they were given purple M&Ms. So this little sentence tells us our interaction effect, right? It tells us each of the means and standard deviations for each of the 4 different groups. Participants who liked chocolate ate an average of 16 M&Ms if they were given pink M&Ms, and ate only 10 M&Ms if they had the purple M&Ms. There's also a significant main effect for those who like chocolate, right? So I'm stating out that there's a main effect for those who like chocolate. That's a specific main effect. Overall, consumers who liked chocolate ate more M&Ms than those who did not. So I'm stating directly in which direction this is going. Which group is greater than the other? Finally, there's a significant main effect for M&M color. Again, same thing. I'm stating that there's a main effect, and I'm stating the direction of that main effect. So those are the elements that are very important when writing up a results section. Okay, so we've gotten through that. We've computed, we've applied the two-way independent samples ANOVA. Now what I want to do is give you an opportunity to calculate stuff yourself and run through your own problem. And so here's a practice problem. You want to know whether IAS students differ in the number of genres of music they listen to compared to other students. So student type. You are also interested in comparing those who play instruments. You have the following information. So you have the sample size, the number of groups for student type, the mean standard deviation, the number of groups for play instruments. You have 2. The mean standard deviation there. And so here's your final results. Go ahead and use the calculations earlier to plug away, and you should be able to compute the degrees of freedom, the critical region, the mean squared, the F value, and the effect sizes. And then also be able to interpret that.